This time is
I wanted to.
yeah.
I think you must be telling me that. Put on the wrist.
Alright. Very glad to introduce Carolyn Zhang, who is on her way from Chicago to Harvard, and she'll tell us about anomalies of non-invertible symmetries.
Okay, cool. So this is a diverse audience, so do ask questions, please.
Is the mic turned on?
Oh, sorry. Hello? Okay. Today I'll be talking about some aspects of non-invertible symmetries, mostly in 1 plus 1D and 3 plus 1D. Most of the talk is going to be based on this paper with Cordova back in April, but hopefully I'll have some time to talk about some aspects of this paper that we're planning to post tomorrow. And the outline is, first I'll kind of set up the problem, which is how do we detect when a non-invertible symmetry is anomalous? And I will specifically, I'll spend most of the discussion on 1 plus 1D, where it's probably more familiar to most of you. And then I will discuss 3 approaches. So the first 2, I won't talk much about the first one, but I will spend a lot of time on the second one. And these 2 approaches are systematic for 1 plus 1D. That means that you can apply them to any non-invertible symmetry in 1 plus 1D, but they're very hard. And then I will discuss some examples, and then at the end I will try to talk about this third approach, which is not so systematic in 1 plus 1D, but it is easier to generalize to higher dimensions, and it is also easier to evaluate. Okay, so let's first define what we mean by anomaly. So I'm going to define an anomaly as anomaly equals obstruction to flowing to a trivially gap phase. And this is a phase that has a unique gap ground state that respects a symmetry on any manifold. So in higher dimensions, we need to specify any manifold. So this is what I'm going to take as my definition of anomaly. And let's review some aspects of our very familiar anomalies of invertible unitary symmetries. So maybe I will use, okay, I don't know how this is going to go. Okay, so for our unitary symmetries, suppose that we do 1 plus 1D. if we have a unitary symmetry G in a bosonic system, we know that the anomalies are classified by H over 3 of G with coefficients in U1. And so this is going to be detected as follows. We can take a simple example. We can take G equals Z2. And in this case, if you evaluate this, this is going to give you H over 3 of Z2 with coefficients in U1. That's going to give you Z2. That means that there are two kinds of Z2 symmetries in 1 plus 1D. One is anomalous and one is anomaly-free. And we can write them very explicitly. So our first kind of Z2 symmetry is just a product. So suppose I work on the lattice in 1 plus 1D, and I just have a chain of qubits. The first kind of Z2 symmetry is just a product of on-site symmetries, spin flux. And the second type of Z2 symmetry is this is familiar as the boundary representation of symmetry in the Levin USBT.
Sorry, what are you writing here?
These are Pauli operators.
These are charges.
Hmm?
Are these charge operators?
These are just Pauli spin operators. They act on qubits. And so in a 1D spin chain, you have the operators acting on each two-dimensional Hilbert space are generated by the Pauli operators. So this is just a Pauli X operator acting on a site J.
Right, but it's supposed to commute, it's a conserved charge, it's a commute
Yeah.
with the Hamiltonian.
Exactly. So in this case, right, you can write down a local Hamiltonian that commutes with this operator and has a unique gap bound state. And that's because this is not anomalous. And if you try to do the same thing with this operator, you'll find that you can't. So there's no Hamiltonian that commutes with this operator and has a unique gap bound state, and then we say that this is anomalous because it can't. You realize you can't realize a gap Hamiltonian that realizes this and is trivially gapped. Yes.
Can you give a continuum example? Oh,
Yeah.
For one of them, yes, and just a massive scalars.
Yeah. So here you can give a compact boson theory where you shift both of the conjugate variables by pi.
That's a mixed.
No, it's a unitary that shifts them both simultaneously. So that's a Z2 symmetry. Okay, so this is so you can't have this Hamiltonian. And
Can you just explain what is written there? There's a product over sigma jx, and what is that symbol between the?
this is the I.
Oh, I to this part.
Yeah. So yeah. And then how do we know that this is anomaly free and this is anomalous just by looking at the symmetry operator site? So what you can do is you can evaluate an F symbol. What the F symbol tells you is if you have two if you take these Z2 symmetry defects and you can imagine a space-time diagram where you're fusing them in different orders. So this is let's call this Z2 element G. This is going to be F. And if you fuse these defects in different orders, you can get a U1 phase. And this U1 phase, so this F symbol is a function from 3 group elements to U1. And it obeys this pentagon equation for consistency. So if you fuse the defects in this way versus fuse them in this way, you end up with the same diagram. So this is a co-cycle, 3 co-cycle condition. And you also want to mod out by co-boundaries. What that means is if you can get this, if you can remove the F symbol by a reassignment of U1 phases to these vertices. So for example, if we can say beta, so you can always modify these vertices by U1 phase. So let's make this very general. A, B, C, and this is A, B, C. Suppose that you can write the F symbol as beta AB. So this is some map from 2 group elements to U1. Beta ABC over beta BC, beta ABC. Then you can remove the F symbol by appropriate redefinition of these vertices. And we say that that's trivial. And when you mod out by those, you get precisely this topology plan.
There are some very stupid people in the audience. Can you explain how you complete that symbol from the formula?
Oh, from these operators?
Yeah.
Yeah, so there's procedures that you can use. So from these symmetry operators, you can get this F symbol. There are basically two papers, Al-Sanayak, and I think it's 2014, and Kawagoe and Wetland, and maybe 2021. And so, yeah, in these papers, it tells you very explicitly, given some symmetry operator, how do you extract that symbol? But you can, there's a procedure to do that.
Thank you.
But, okay, I mean, I could go into that, but I feel like it will,
It's okay.
yeah.
I'm the only one, so.
I don't think
We're not the only one. Well, then speak up.
Yeah.
we're speaking up.
Sorry, what's beta again?
So beta is saying that this is some function from two group elements to U1 because you can always modify these vertices by U1 phase. That's a gauge transformation. And so then this is saying that if the F symbol can be canceled by appropriate gauge transformations, then it's trivial.
Can I try to make sure I understand?
Yes.
Think of these as basically potentially coming from some local countercurrents.
Exactly.
At vertices.
Yeah, exactly.
A thing that you can cancel by local countercurrents is not really.
I think maybe I missed something from like, what is the object? What is the ABC here? Like, are these the symmetry operators, and we're multiplying them in different orders, or what is
Yeah.
the
So these,
choice being reflected by the CP?
so you can think of these as symmetry defects, so they label group elements in this case.
So, but so not in terms of how to compute. I understand you don't like you shouldn't spend time on telling us how to compute it, but what is the thing? How to set up the computation of which the result gives without doing the computation?
Yeah, so you can take this symmetry operator and you restrict it to a finite interval. And then you look at how those restrictions interplay with each other.
And in that setup, what is then these two left and right hand sides? So
So this is saying that in time, you can fuse these symmetry defects, and that will give you an AB defect. Then you fuse a C one in. Yeah. That means that you basically act on this part of space with a C defect.
Thank you.
You guys have defects actually, so the product over J greater or equal to some value?
Yeah, so for example, for this one, you'll multiply sigma x on this part of this chain.
J round over half.
Yeah, yeah. So that's when you restrict the symmetry operator to everything.
So because time evolution is involved, presumably this population involves the couple as well.
Yeah, so you can, well, you can just do it with a kind of sequential application of operators. So this is not, you shouldn't really think,
But
yeah.
how do they change it?
Well, so for example, you can apply the C defect on this part of space. And then, okay, yeah, so there is a procedure that's discussed in this paper where there's various shift operators and splitting operators that you can use to move these defects around. But,
But here it's a Z2 symmetry, so there's only one non-trivial operator. Can you just explain to us how you define it?
Yeah, so here-
GGG.
so here you have GGG
What is
equals
G?
plus 1. This is a Z2 element.
Okay,
This is the only non-trivial.
so it's over all space then, over product over all J's. Because you were talking about some restrictions of J's.
Yeah, but this is saying that you can restrict the Z2 element to act on a patch of space. And then you can have Z2 domain walls and look at how the Z2 domain walls fuse. Suppose you're in a symmetry broken phase and you want to look at how the domain walls fuse in the symmetry broken phase. So then you won't act on the symmetry in all of space. To create a domain wall, you have to symmetry operate on part of space.
You don't like the space, you put it tight-like.
You can also cut it time-like, or you can act on part of space. So if you start off with a symmetry broken phase, you can act the symmetry on part of space to create a domain wall, right? Yeah. That's what I'm talking about.
Are you trying to explain how to extract anomalies from the lattice? Is that the subject?
No, I'm not trying to do that. I will refer to these papers if you want to.
But people know how to, people know how to compute these anomalies, right?
Yeah, yeah.
So what are you trying to show?
So I'm trying to tell you an example of a familiar anomaly so that we can then ask why is this hard to generalize to the non-invertible case? Okay, yes.
I think this question's been asked already, but I
Yeah.
can understand it. So for Z2,
what's the difference between ABC on the left and ABC on the right?
Oh,
They're all
in
the
D2
same.
they're all, well, you could choose A, B, C to be either one or the single non-trivial element for D2
Either identity
or G.
The identity presumably doesn't, when you fuse the identity without anything, presumably you just get.
Yeah, so if any of these labels are identities, then this is fine.
So what's the non-trivial one that has an F?
Yeah. So here
Or G.
you can show that this is the case, and you can't remove this with any reduction.
And what I don't understand is what's physically the difference between doing the thing on the left and doing the thing on the right?
They look the same. You're fusing two G's and then you fuse the third G, or
Yes.
fusing these two G's and then fuse the third G. It sounds like
Just an internal ambiguity.
Yeah, it's
I got these three things sort of arranged on the line. And
Yeah.
It's a question whether I do the two on the right first or the two on
No,
the
it's
left.
an adiabatic. You first do it the left, like on the left side, and then you slowly move B to touch C, and the phase jumps. It's an adiabatic state. It's like about the state about the wave function in the presence of the steps.
I see. So if I move B slowly to the left or slowly to the right, I will get
Yeah,
to the
yeah,
different
but
Yeah.
you have to cross some kind of bad point in the middle, or
Yeah.
there are four lines, and it leads to a phase transition.
Yeah, it's just like when Michael's talking about the traps. You're trapping the anions and you can break the anions. Here you're trapping symmetry defects and you're fusing them in different orders. And you kind of pick up like a phase.
Yeah, it's an adiabatic state.
Yeah.
It's a question of what different orders mean, but it means whether it's the things on the left or the things on the right that are different.
I think what he's saying is in one picture, this vertical direction really is time. And you have three domain walls labeled by A, B, and C. And in one picture, you first split. This is a splitting, not a fusion. You split C off from whatever, AB. You start with a single domain wall, ABC. That's at the bottom. Okay, you split it into A, B, and C first. Then you split AB into A and B. Then the second process on the right, you take ABC, you split it to A and BC, and then split it. So there are two separate processes that differ by a phase. The end result must differ by a phase, and that's F. That's one way to interpret it.
Yeah, it can differ by phase.
Yeah.
But it does, and you can't remove it, then it's an anomaly. One can show that this anomaly is related. So now if you have different fusion of domain walls giving you rise to these phases that you can't get rid of, if you try to proliferate the domain walls to arrive in a symmetric state, then you will have these ambiguities and you can't get to that state, which is why you can't realize your trivial gap phase. Okay, so now this is nice. We know that if we have a group-like symmetry, all we have to do is compute this F symbol, which we can do, and then we need to check that it's not a coboundary. And if it's not a coboundary, then we know it's anomalous. Okay. But now we know also that there are more general non-invertible symmetries. So for example, in ISO-CFT, we have maybe I'll call this F and sigma, and these obey non-invertible fusion. So for example, we have F times sigma equals sigma fused with F in sigma, and we'll still have sigma times sigma equals 1 plus F. And in this case, we can also have an F symbol. What we have is going to be something like, now we have A, B, C, D, E, and this is going to be a sum because there can be multiple fusion outcomes. EF. So we have now a sum. And this is no longer going to give you just a U1 phase. So you can't say, oh, you get a U1 function from G times G times G to U1, we just need to check it's not coboundary. Now it's kind of unclear what the analogous story is in this case, so that's kind of why it's not trivial. In 1 plus 1D, this is the structure you'll get. And first I will talk about how we'll be able to detect anomalies for these more general fusion category symmetries, which can also be realized in quantum systems, and can also lead rise to constraints on dynamics and be very powerful mechanisms.
Is it true that all non-invertible symmetries will have a non-trivial associator? Will F be non-trivial?
Depends on what you mean by non-trivial.
Not equal to 1 modulo the gauge transformation.
Well, it has to be unitary, right? So if it's a matrix, then there has to be some non-trivial matrix elements. It can't just be 1, 1, 1, 1, right? Yeah.
So this fusion algebra can detect only anomalies that are valid in H3, because we know that there are also anomalies that are valid in the cobordism group.
Yeah.
So can you actually see this using this picture, or
Yeah.
beyond this picture?
Yeah, so those are beyond this picture here.
Okay.
I will talk about, in 1+1D, we will talk about still, well, in 1+1D, these are completely classified. There may be also kind of different classes of non-invertible anomalies as well, which I'll only talk about some of them. In 1+1D, the method is kind of complete, just like how this F symbol method is complete.
So why is it important for non-invertible symmetries to have some here?
Oh.
What is the
It's important because in non-invertible symmetries, the part that makes it non-invertible is that you can have a fusion that has multiple outcomes. So that means that this is non-invertible because there isn't any element that if you fuse it with sigma, you just get a single vacuum. Right? There are multiple outcomes, so that means that this F can take value in different things, so that there's a sum. Okay. Yes.
So do you understand what the Hilbert space is on which these non-invertible symmetries act? What is the control Hilbert space?
Yeah, so for example, you can find these in various CFTs. Like the Ising model at criticality, which has a tensor-firing property.
Well, but there the symmetry is merged, right? Or
Yeah. So, okay. So that's a question of where do you find these non-invertible symmetries? You can also find them in, say, like anion chains, which have some sort of constraint.
but is there no answer to the question about, like, in general, do we need some kind of non-local product, non-tensor product Hilbert space for these anomalous symmetries to act with,
Yeah. So.
or I will adopt kind of a more continuum equal whatever. Just
Yeah, you can, for the purposes of this talk, you can think of a more continuum description.
The Ising model of criticality, that has a non-invertible symmetry that's on the lattice though. It's not described by Ising fusion category that Carolyn wrote, but it's non-invertible. The Ising model of criticality, 1+1D, can just build the Ising model. There's an operator that commits to the Hamiltonian that is non-invertible.
Yeah, but only if you choose the transverse magnetic field to 1.
Yeah, so at criticality, that's
At criticality, there is an exact non-invertible symmetry on the lattice.
This is the one that like squares to something times the translation.
but that squares the translation.
Which is not exactly this
That's
fusion.
not that's
It
not
doesn't obey this algebra.
but that squares the translation.
No.
Yeah, but it's not invertible, it's just, yeah, in the IR, yeah, it's
There are 2
described.
points of view on that. One is that you double the Hilbert space, and then it squares to a translation. Another point of view is you don't double the Hilbert space, and you double the Hilbert space, and then you get that, or you don't double the Hilbert space, and it squares to a translation. These are the 2 lattice models that we made in the relationship.
If double the Hilbert space, that's enough.
Yeah, then you get this algebra.
Double the Hilbert space means you have Ising cross Ising.
Yeah.
You can think of it as like having the original matter degrees of freedom and also the gauge degrees
This is
of
like
freedom.
for us and collaborators.
Yeah.
Just a very quick question. So these F's here, the modulus of them is presumably coming from some fusion category rules or whatever it is, and the phases are supposed to be anomalies. Should I think of these F terms like that? That the phase is the anomaly, and but the modulus is something which defines the non-invertible symmetry.
Yeah, so there's going to be constraints on the F symbols coming from the fusion algebra, which I will discuss in a moment.
Right.
Yeah.
And then the phases should be the anomaly related. Or
There can also be anomalies related to just the fusion algebra. Yeah.
it's not just the phase.
Yeah. For non-invertible symmetries. For example, you can show that if the fusion algebra gives you some element with a non-integer quantum dimension, that doesn't take any information from the phase of that symbol, but it will still be anomalous. Yeah. Okay, so let's define what we mean by non-invertible symmetry. In 1 plus 1D, I will define it for 1 plus 1D, and then there are generalizations for higher dimensions. We need several pieces of data, right? So the first piece of data are the simple objects, which I will label A. In the script-like case, you can think of these as, so let's call this, in 1 plus 1D is a fusion category A, and in this invertible case, you can think of A as lying in the group elements, or some group, unitary group. And then there's the fusion algebra, so we have A fused with B is going to be a sum of other elements C with some fusion coefficient. And associated with this fusion algebra, you can have a quantum dimension. As I mentioned, that can also give you anomalies. But this is just some integer or some number that you assign to each of your elements of your fusion category that also obey this equation. And I should mention that you always have a vacuum contained in these simple elements. And for every A, there's a bar such that A times A bar is equal to 1 plus maybe other things. And in the abelian case, in this invertible case, all of these quantum dimensions are 1, because the dimension of that vacuum one is 1, and then that means for any EA, you can have an EA bar equals, this 1, so all these dimensions are 1 in the invertible case. But in the non-invertible case, these can be more general. And then finally, we have our F symbol. I won't write it again. But these are the pieces of data that define your non-invertible symmetry in 1 plus 1D. And we want to understand from these pieces of data, how do we know whether or not the future category symmetry is anomalous? Yeah.
Sorry, are you exactly how are you defining the quantum dimension? Is it expectation value of the line?
Yeah. Like, yeah.
And for invertible symmetries, it has to be 1 and can never be like minus 1, because the idea is if you make the line this loop very small, it looks like an intensity of some.
So there are certain conventions that some people take where if you have something called like a non-trivial Frobenius shear indicator, sometimes they then put it onto this dimension so they have negative dimension. I'm going to take the convention where we always keep them to be positive. Yeah.
Is the physical motivation what I said? Basically, if I have a topological line operator, I can just make it really tiny, and then that looks like a trivial operator.
For invertible networks, and what fails for non-invertible? Still some point.
Oh, I don't know. That was going to be my follow-up question. But
Yeah, because it can fuse into multiple different outcomes.
okay.
Yeah, so when you shrink the non-invertible operator like that, which is contractible, you get some non-trivial point of it.
So
Because they're non-invertible. So they don't, it doesn't annihilate itself.
you can't just get the vacuum.
So it's a non-trivial operator.
So I thought you don't get the vacuum times in double. Yeah.
Okay, yeah, so
you get the vacuum times.
You just get the vacuum. Yeah.
Okay.
It's multiplied by number. That number is positive, right?
I see. So there's no natural normalization of
It's just
these operators.
there is none.
I see.
It's giving the
Because for invertible symmetries, you always have a set of unitary operators, and they don't change the normalization of the vacuum. But for non-invertible symmetries, there's no natural normalization of these operators. But there are these numbers.
But it's giving the vacuum. Yeah, it's giving.
Right.
Okay. So this is our data, and we want to understand when the symmetry is anomalous, given these pieces of data. And there are multiple different approaches. And the first approach, I'm going to call the edge approach. Just develop it.
Sorry, it's a bar unique.
Huh?
It's a bar unique.
Yeah, there's a unique A bar. Yeah. So the first method is an edge approach. And I call this an edge approach because the other two, number 2 and 3, both require some data from a topological order 1 higher dimension, which can be thought of kind of as an inflow theory. But this one requires only the 1 plus 1D theory. And 1 and 2 are specific for 1 plus 1D, so that's another point. And this is the statement that A is anomaly free if and only if there exists something called a fiber functor, which I won't get into much detail about because this won't be the focus. But basically, and I should say these ASPTs, which are invertible phases with asymmetry, are in one-to-one correspondence with such fiber functors. And this is the approach that was taken in, well, I guess, EJNO, and Tachikawa. This is the tensor categories book, and also Thorngren and Wang. And this is a brief sketch of why this might define an invertible phase that has this symmetry. This is basically a map to a category with a single simple object. So you can think of it as you have these elements which label objects of your symmetry, and you also have these boundary labels. And they also obey some kind of fusion. This is going to be looking like this. Alpha, C, gamma, alpha, beta, gamma. And you can think of these as labeling the degenerate vacua in a symmetry broken phase. What it means to have a single simple object means that all of these labels are the same. And so you can think of that as having a unique state no matter how you act with the symmetry. So this is going to be like an ASPT because it has a unique state. So that's the intuition behind fiber functor.
What do these pictures mean?
So this is the boundary. This is your 1D theory. You can think of alpha as labeling kind of the
Boundary condition?
the state, the different vacua. If you have a degenerate ground state, right, then you'll have different labels here. Because when you act with the symmetry on part of it, then that will change the state. But if you have a unique state, then all these labels are the same. So that's the idea of a fiber functor.
I still don't understand what that line is supposed to specify a finite system with some boundary or what?
Yeah, so you can think of this as kind of the spatial direction along this vertical direction. Yeah.
The spatial direction.
Yes.
Oh.
Yeah.
And this is time.
Yeah.
This is time.
Yeah.
So it's a.
Or sorry. You can think of you can think of you can think of either as space or time, but this is saying that you start off with a state alpha, and then when you act with the symmetry, you get to a different state beta if there's degenerate ground states, or you can get back to the same state alpha. And here it's saying that you always get back to the same state, so it's a unique.
Well, if the symmetry is spontaneously broken.
If it's spontaneously broken, then you'll have different labels here.
Right.
But here we're saying that this fiber functor means that you can label these with all the same labels, so there's a unique state. And when you can find such an object that's compatible with certain linear equations that this has to satisfy, then the symmetry is anomaly free because you can construct this object.
So, but there's an assumption of gap state. I mean, because you could imagine that you have an anomaly still and acting with operators. It's completely unique ground state, but saturated by some gap of CFT.
Yeah, and I'm assuming that yeah.
Okay, so the statement is if there's a self-consistent solution to this, then there's no.
Yes. But this is really hard because this participates in a nonlinear equation, and it's hard to show that such a fiber functor exists.
So M and F satisfy some nonlinear.
Yeah, it's something like some F equals M. Kind of like how this equation is like F equals F.
Mathematically speaking, is alpha a module or your tensor category?
Yeah, so this is a module category with a single simple object. Yeah.
So earlier, the other pictures you said I could interpret as domain walls of some symmetry broken state.
Yeah.
So should I interpret here as you're shoving domain walls
Onto the
on
boundary.
an SPT, you're trying to absorb domain walls into an SPT? And
This is saying now we're trying to act as symmetry on your 1 + 1D system,
so just
which creates domain walls in your 1 + 1D system with this. Yeah.
just to connect, to, you were mentioning ASPTs.
Yes.
So I thought the alpha was labeling my state of my SPT? Or?
The A labels the symmetry, but you can have many SPTs of that symmetry, right? So for each solution, you get a different invertible phase with the symmetry, and those label ASPTs.
But the alpha was labeling the ground state of the SPT?
This is A.
But the alpha on the line?
Yeah.
Boundary.
I guess I'm a bit lost. Maybe I can phrase it differently. So earlier I had the interpretation there of domain walls of symmetry broken state.
Yeah.
Should I again interpret this as domain walls? Or how should I physically interpret your recent picture?
Yeah. So you can so this is saying okay. You can also think of this as the boundary of a topological order, where you have kind of a unique state under that symmetry, and then these are now you're shoving into these boundary states. But you can also I don't know if that clarifies.
Could you think of it as like on one side it's an SPT? Let's say on the right side it's no, maybe on the left side it's an SPT, and on the right side it's symmetry broken. No, which one's which? Left side symmetry broken. So those are domain walls in some symmetry broken phase, and the right side is an SPT. He's describing a junction between a symmetry broken part and an unsymmetry. Is that correct? You know what I'm saying? Like this solid line that's going up, labeled by alpha, is actually a boundary between a symmetry broken phase on the left and a
Yeah. So that's it. Yeah.
and these are domain walls that are coming out of that boundary. Does that make sense?
Right. I'm thinking about this alpha as labeling. So okay. Are you talking about left and right hand sides of this? You mean?
Yeah, I think he was asking, and I didn't know if this was the answer, that the left side might be a symmetry broken phase.
Yeah.
A, B, and C are like kind of like defects in that symmetry broken phase. And the right side is like an unbroken phase. And then this is like some consistency about I can bring domain walls, I can move domain walls out from this junction. You know, I can bring them out, or I can in different ways, and I have to be consistent, and that's what this equation is saying.
Yeah. So you can also think of it that way.
Why do you need to get a single alpha then? It's better to already grow.
So the point is, I think this should be anomaly free.
Okay, how do you
If
think
it
about
has a
alpha?
solution.
I guess Max, if the symmetry is broken, there's no edge mode, so I guess it's still unique on the right hand side. If this symmetry here, all the degeneracies in domain walls then?
So you have it now. Okay. So if you think of this as a space direction, and you have this is the symmetric phase, and then this is some other symmetry broken phase, then yeah. So then you will have different labels for alpha. You can't find a single solution. Yeah.
Just a notation. So that M thing should not have any labels other than A, B, C, and alpha. Is that correct?
There's also a label of yeah. It should only have so all these.
Beta should be an alpha.
Yeah. So these should all be alphas.
In your
And just language-wise, is M the fiber functor, or is it something else?
So M is kind of this collection of objects with this symbol. And,
A physical way to understand it is that if you can say A is anomaly free, if you can gauge A, you get a trivial phase. So then this is like the set of equations to have a consistent boundary with a trivial phase. So if there is a solution, then A is anomaly.
I'm just trying to see if I understand this notation. So the sum over alpha doesn't mean anything because there's one alpha.
Yeah. So here
There's
there's
no
no sum.
Good. And so M is your fiber functor, is that correct?
Yeah, so it's gonna be this M symbol is gonna be defining your fiber functor.
I see. And so if it exists and can satisfy this equation, then it's
Yeah,
not
there's also other data. Like there's gonna be there's gonna be some in general some vectors like some non-trivial dimension here, and so this is simplification. But
Thank you.
okay. So this is the edge approach, and it's kind of hard because it's hard to find a fiber functor. And it's hard to have kind of a on-thought for what a fiber boundary should look like. And so there's another approach, which I will call a bulk approach. Actually, that says the following. So this is the bulk approach. And the idea is for every fusion category A in 1 plus 1D, and the idea is this also generalizes to higher dimensions, there's a corresponding topological order. So this is 1 plus 1. There's a corresponding topological order given by the center. This is going to be in 2 plus 1D. And the statement is, so this is some topological order in 2 plus 1D, and it's uniquely defined given this A. And the idea is A is anomaly free if and only if there exists a special kind of gap boundary of this topological order. So this is going to be a topological order, and its gap boundaries are enumerated. Gap boundaries are labeled by Lagrangian algebras, which I can discuss in a moment. But you can think of this now as just some data that defines what kind of anyons can enter the boundary and defines the gap boundary of this topological order. And if there exists a special kind of Lagrangian algebra that I'll call magnetic Lagrangian algebra, and the idea is as follows. If you take this Z of A, which is a 2 plus 1D topological order, there's always a uniquely defined always a uniquely defined electric Lagrangian algebra. It's uniquely defined because whenever you specify Lagrangian algebra, that will tell you what anyons can end at the boundary. And then the anyons that are not allowed to end correspond to low energy excitations near the boundary. And those can be thought of as domain wall excitations, which form a fusion category. And the electric one is the one that says that that fusion category is precisely A. And it's uniquely defined because for any symmetry, there's a unique, completely spontaneous symmetry building case. Yeah.
You say those words again.
Yeah.
Can you explain what the picture?
What is a Lagrangian algebra and what makes it electric or magnetic?
Yeah.
Is there some simple version of this?
Yeah. So the idea is the electric one. So this is going to be some collection of anyons. So the Z of A has some defining data, just like how the fusion category has some defining data. It has some simple objects, which I'll label A tilde to differentiate them from the simple objects of the fusion category. They also obey some fusion. And they have F and R symbols, which I'll call F tilde and R because this is not the same F symbol as in the fusion category. So, for example, for a physical construction, you can take the fusion category A, compute the string net model, and that will precisely give you C of A. We can take some examples. So whenever your fusion, some examples are if you have, for example, A equals back Z2, because it's some cocycle omega. So this is just the Z2 example that I gave earlier, where this is, well, I can just call this our F symbol. This is the Z2 symmetry with some possible anomaly. Then Z of A is either Z2 gauge theory or Z2 gauge theory, depending on this F. So now we can consider the gap boundaries, and in general, this gap boundary is going to take some form. It's kind of like a composite anion with some integer labels and A. Basically, this says that this A anion line is allowed to end at the boundary, and it can end in NA different ways. So this labels some maybe different ways to annihilate your anion at the boundary. Okay, and so you need some NA dA equals the total quantum dimension of the topological order, which Michael discussed. This is just the square root of the dA squared. And that ensures that all the anyons that can't end at the boundary are confined. So then you're left with all the so you use an anion can either end at the boundary or is confined by the ones that are ended at the boundary. So this is the information that defines the gap boundary of this 2 plus 1 topological order. And yeah.
Just some vague exhibitions really. When you think about Drinfeld centers, it's a bit like taking a tangent on them. And that's where Lagrangian comes from. So there's an obvious Lagrangian, which is the thing you start with, base.
Yeah.
But there are others as well. There might be others as well. It's a bit like, Neumann-Dirichlet boundary conditions.
Yeah, so this would be like Dirichlet boundary conditions.
Inside it.
Is this going to be important for the rest of the talk?
Yeah.
I think you're going to have to go through it again in more detail because I think I'm completely lost. If I'm alone, people can tell me to shut up. But
maybe give you an example with like the F theory or something.
Yeah. So for example, in this Z2 gauge theory, we can do an example that I think might clarify things. So in the case where you have a group, then this is just going to be Dirichlet boundary conditions for the 2 plus 1 gauge theory. So if we take Z2 gauge theory, so Z2 gauge theory. Okay, maybe I'll start with the symmetries. So we know that there are 2 kinds of Z2 symmetries. So the first one is vec Z2, and then I'll call this F0, which is the trivial one. And then the second one is vec Z2 with a non-trivial one. This is the F GGG equals minus 1. And then
we're talking about Z2 gauge theory in how many dimensions?
2 plus 1.
2 plus.
So if you now take the center, then this will be Z of vec Z2 F0. And this is just untwisted Z2 gauge theory, right? So this is just a topological order that has anions 1 and EM. This is just like K matrix. Yeah.
So if you were to write an actual Lagrangian,
Yeah.
it would be BF theory.
Yeah, it would just be like B, D, A.
But this use of the word Lagrangian has nothing to do with other uses.
Huh? No. This Lagrangian is not any
Nothing to do with
Lagrangian.
Lagrangians I know and love from grad school.
No, yeah, so you shouldn't think of this Lagrangian as a Lagrangian. Yeah, so then this is, and then this will give you vec Z2 F1. This is going to be a theory where now the M is a semion, so it has topological spin I. Okay, in both of these cases, so this one, LE, in the case where you have abelian topological order, you can instead study them with Lagrangian subgroups. So a Lagrangian subgroup, which I can call L tilde to differentiate them from Lagrangian algebra. Yeah.
So number 2, that Lagrangian is U1 level 2 times U1 level minus 2.
Yes. Okay. And then this is well, first it's a collection of anions within the whole set, such that theta AB equals 1 for all AB in this Lagrangian subgroup. And then second is theta AB is not equal to 1 if for any A that's not in your Lagrangian subgroup and B in your Lagrangian subgroup. So that means that these are a collection of anions that you can kind of condense simultaneously, and the ones that are not condensed are confined because they break non-trivially with the ones that are condensed. So now we have our electric Lagrangian subgroup is just generated by 1 and E. This is your gauge charge. And in this first case, you have a magnet. So okay. So now is this clear now what I mean by this gap boundary condition for this particular example? So
stupid question, like what is beta AB?
This is the rating between A and B. Maybe I should label these A tilde, B tilde because they're in your topological order. Yeah. So for a bosonic topological order, also the ones, and you need
So this Lagrangian L is defined as anions which braid trivial. Is that claim?
All of the ones in your subgroup have to braid trivially with each other.
Right. Okay, so that's the definition of this Lagrangian.
Yeah.
Why is it called Lagrangian?
So the Lagrangian condition means basically this. I don't know why they call it Lagrangian condition, but
Lagrange knew all of this.
yeah. So it's basically this condition because you could get a collection of anions that braid trivially with each other, but it doesn't satisfy this condition, and then you would call it Lagrangian.
So, and what is D? What is capital D?
This is the total quantum dimension of your topological order. So here, right, as Michael said earlier, it's going to be 4 because of the square root of 1 plus 1 plus 1 plus 1. It's 2 because of the square root of 1 plus 1 plus 1 plus 1. And you can see that this has 2 elements, which satisfies that requirement. Okay, so now, okay.
Just to make sure, so as long as you define NA short, so that that equation is satisfied, then that's another definition of the equations.
If you can find a what?
NA short. So
This one?
Yeah.
Yeah, these have to satisfy certain consistency equations.
So there's
But there's also additional data that defines the Lagrangian algebra, which I haven't. There's some nonlinear equations that they also have to satisfy.
it seems there are two definitions in the blackboard.
Yeah, so this is the definition used when you have non-abelian anions. This is the simplification if you have abelian anions only. Yeah. Because then really the anions you confine are just, like if you have abelian anions, then your anions form a group, and then you just condense a subgroup of those anions. And then for non-abelian anions, then it's more complicated and you need this additional structure.
So that is still not clear to me. Returning to the M, returning to the magnetic ones.
Yeah, so that's what I want to define. Okay.
So this previous one on the left side of the board, is this electric Lagrangian subgroup?
Yeah, this is the electric Lagrangian subgroup. Yeah.
Okay, thank you.
And now, if we define this topologic, now this thing on a cylinder, and we choose this to define the boundary conditions of both sides, that means that, for example, in this case, your E anion can tunnel across your system because it can end on both sides. And now, what we want to do is we can shrink this so it's effectively like a 1 plus 1D system. And your E anion can still tunnel across. And you still have this fusion category A, which can, in this example, you can think of it as the M anion when it comes to the boundary, it becomes confined. And so it forms a fusion category A, which is density 2. And that fusion category here, in this particular case, you can really think of it as kind of given by the emerald line. And that symmetry is spontaneously broken. And the reason is, if you have E that can tunnel across, that forms a you can insert it at 0 energy cost, right? And so it gives a non-zero order parameter because it breaks non-trivially with the M. And so now this defines the phase. If you have this topological order and you squeeze it to a 1 plus 1E system, and if you choose Dirichlet boundary conditions on both sides, then that corresponds to a 1 plus 1E system where this fusion category symmetry is actually completely spontaneously broken.
What does Dirichlet here mean? You're very abstract in general. I mean, you haven't introduced fields and Lagrangians.
Yeah.
What do you mean by Dirichlet boundary?
What I mean by, so, okay, that's for gauge theory, you can think of it that way, but we'll have more complicated ones, but I just mean the gap boundary such that when you now, the gap boundary that corresponds to the 1 plus 1D phase where the fusion category symmetry is completely spontaneously broken. And so in this case, this LE, if you can then choose that gap boundary for both sides, then that will give you a 1 plus 1D theory where this fusion category symmetry is completely spontaneously broken because there's a non-zero order parameter that gains there's a non-zero order parameter. And it's an order parameter because it's odd under the symmetry because because it raised non-trivially. In this case, you can think of it as grading non-trivially with the envelope line.
So directly means the same thing as like a equals 0 on the boundary.
Yeah.
And the Wilson line can end on that boundary because a is equal to 0 on that boundary, right?
Yeah. You seem unsatisfied, but
It's okay. It's okay. This is not, I think, very important. It's some kind of boundary.
yeah.
Maybe a better question is, why is all of this formalism important for? I guess we're gonna go into that.
Yeah.
For this. For defining an anomaly. Am I correct? You want to define an anomaly for non-invertible symmetries, or what? Or is this already defined?
Well, this is important because I need LE to define LM. So LM, the definition of LM is another gap boundary, and it intersects trivially with the electric one. So the only anion that's contained in both is the vacuum anion. And that's important because now, if we draw this picture, we can replace this by M. But now, because the E can't end here, because it's not contained in this Lagrangian algebra, it can't tunnel across. And now when you shrink this thing, because there's no order parameter, because this E can't tunnel across the system, this A symmetry is actually, this fusion category symmetry is not spontaneously broken at all. And here, right, in this D2 case, we can say, for this particular case, LM is 1M. And in this case, because this is a semyon, it can't condense. So that means that there does not exist a magnetic Lagrangian, so no LM. There does not exist a Lagrangian subgroup that intersects trivially with this one that you've defined. And then when there does not exist such an object, you can't do this construction to construct a 1 + 1 E theory that has the fusion category symmetry, but has no order parameters, so it doesn't break it.
And should be clear why it's an if and only if? Because you explained one direction, I guess, right? That if the LM exists, I understand how you can create the gap trivial phase, but you're saying it's an equivalence?
Yeah, so if the LM exists, then you can construct this. And if you have a 1 + 1 D theory, okay, then that has a unique gap ground state, then you can, there should be a way to extract an LM.
You're saying because all boundary, like any limiting process must have been, there must be some boundary condition existing to explain it?
Yeah.
I see.
And I should say that there may be multiple LMs, and that will give different SPTs. And so, for example, if you have Z2 times Z2 cage theory, right there you have anions generated by E1, M1, E2, and M2. And there your L tilde E is 1, E1, E2, E1, E2. But you have two LMs, right? You can have LM equal 1, M1, M2, M1, M2. And you can also have 1, M1, E2, M2, E1, M1, M2, E1. And these both intersect trivially with this one, and that just tells you that 1 + 1 you have Z2 classification, Z2 times Z2 SPTs. Yes?
Can you maybe talk a little bit more about how the fusion algebra, the symmetry, the members in this thin cylinder structure?
You mean how the asymmetry is there? Yeah, so whenever you have anion, Lagrangian algebra, that will define a gap boundary that comes with the fusion category. Because there's going to be some, the other anions, when you bring them to the boundary, if they're not in the Lagrangian algebra, they get confined. And so then they form low energy excitation. So for example, if you choose to combine the E, the M raised non-trivially with the E, so it becomes a local excitation near the boundary that then forms, you can think of it as if you nucleate two M's and you bring them all the way around, that forms a domain wall of that symmetry. And so it forms a symmetry A. In general, it's actually kind of complicated given an anion in the bulk, and you bring it to the boundary, what kind of boundary excitations it will become. But it's believed to form a fusion category.
Oh, in the level 11 model,
Yeah.
this is the rough boundary, I think, this is smooth boundary.
Yeah, so it will be like the rough boundary of the quantum double or smooth boundary of 11.1. Yeah.
So I think of A as the kind of boundary excitation, which kind of domain walls of this.
Yes.
Of this
Yeah.
like,
Yeah.
Is there a way to think about the Wilson loops going around the cylinder? Is that a way to think about?
Yeah, so here you'll get another symmetry on this boundary defined by Lm. So here you can have the symmetry and a stool symmetry are both there, and they're both not spontaneously broken because none of the anions can tunnel across.
Just for the just in terms of the action of this symmetry. Right, so you were talking about the domain walls before. Is there a natural way that you get symmetry on the surface?
Yeah, so you can, if you nucleate two domain walls, like the MM bar, and bring them around, that will be like the symmetry operator for the entire 1+1 system.
So shouldn't it go out?
That would be two, well, in this case, yeah. Okay, so,
I have to ask one more question.
Yeah.
So, I mean, what is the, how do you define LE as opposed to LM generally? Is this just for this particular Z2
yeah, so it can,
series, or I mean, generally, can there be multiple, L's which mutually just intersect with identity and they have trivial grading?
yeah, in general there can be multiple LMs, but there's a unique LE, because there's a unique, fully spontaneous symmetry broken phase. So this, as was mentioned earlier, if you think of the stringnet model, this is kind of the gap boundary that the stringnet model came. Oh, okay, I'll just say that this is uniquely defined. Because this phase is this.
So what's the defining property of LE? Right. No, but I mean the LM has the same property that they mutually grade trivially, right?
Yeah, so this is satisfied by any Lagrangian subgroup. But there's a uniquely defined one given a symmetry A.
Okay, the symmetry A.
The A uniquely defines it. Yeah.
You have to specify what is the symmetry.
Yeah. Okay. So in general, this is also hard because it's hard to say, you have to go around searching for this object, which is in general hard because it has to satisfy some nonlinear equations, kind of similar to the pentagon equation. But the thing to notice is this is a bit more intuitive because we know that all of the anions that are in this LM, so all, as I mentioned before, these get to form kind of as a sum of different anions in your topological order, and the sum of NA, DA is D. We know that if we have an LM that intersects trivially with LE, then there needs to be enough bosons in your theory, because all of the anions that are in this Lagrangian algebra, all these A's are bosons, right? Because you need to condense them. So that means that if you don't have enough bosons you will always have enough to create this LE, but you may not have enough left over to have this LM, because these coefficients come with certain constraints. So it may not be possible to satisfy those constraints and this have enough bosons in your theory. So for example, in this case, right, we know that we have total quantum dimension equal 2, and we want to have 2 Lagrangian subgroups that intersect only on the vacuum. So that means that we need at least 3 bosons. And in this case, we certainly have 3 bosons. And in this case, we only have 2 bosons. So without even trying to find Lagrangian algebras or Lagrangian subgroups or anything, we can see that this has to be, this with the non-trivial cocycle has to be anomalous And the reason is the corresponding multi-topological order doesn't have enough bosons for both of these gap boundaries to exist. Okay, so that certainly doesn't prove that this is anomaly free, but it indicates at least that there's no, sometimes counting bosons can give an easy kind of obstruction for the fusion category symmetry to be anomalous, or anomaly free, yeah.
Why choosing n1 equals 2 is not a Lagrangian? Like, so you have just the trivial line, it's not a Lagrangian algebra?
Yeah, so there's certain constraints. So some constraints are the coefficient of the vacuum line is always 1. Another constraint is n A and B is less than or equal to n A, B, C, and C. And then, so these are some constraints that then sometimes it would make it hard to construct something that has this dimension if you don't have enough bosons.
Okay, so I think it was actually we take some minutes rest, okay, for people just to maybe come back. Maybe 7 minutes or so.
Yeah.
How do I mute? Oh.
This one is
Yeah.
from the computer.
So I would like to talk about a particular kind of family of 1 plus 1D non-invertible symmetries. The reason why I'm going to talk about this family is because they're going to nicely segue into the method 3. The idea is that we can have Ising fusion category, which is basically G equals E2 together with the duality defect sigma, but we can generalize this to other abelian groups. So we can take any G abelian group G and also add a duality defect, and that will give you something called the Tabarino-Montgomery fusion category, but you can think of it just as generalization of Thomas 1U. And these two objects encode the F symbol. So, for example, I'll just tell you the fusion rules. So, or let's first define a simple object. The simple objects are your group elements together with sigma, right? And their fusion is just, well, H equals PH. They have just your normal group-like fusion. And then the sigma absorbs all of the group elements. And then your sigma times sigma is the sum over the group elements. And so that means that the prime dimension of sigma is the square root of the order of the group. Because you're going to, all these have dimension 1, and then this is like U sigma squared equals G.
Are there any generalizations of this kind of stuff to continuous symmetries?
Yeah, so I should have mentioned in the beginning that I was only going to consider finite internal symmetries. In the continuous case, well, this kind of formalism, rigorously speaking, applies to the case where you have a finite number of simple objects. But people have also studied continuous non-invertible symmetries. But I'm going to restrict it.
And the group is going to be abelian?
It has to be abelian. At least, so in the abelian case, you can show that the F symbol, if you solve the pentagon equation, the F symbol has some simple to enumerate solutions. So for example, you have F, G, sigma, H, sigma, sigma, sigma is GH. And this is a symmetric bicharacter. So that means that this is some function from two group elements to U1 that satisfies chi GH equals chi HG and chi GHK equals chi GK, chi HK, etc., etc. So this is some function that satisfies certain properties, and you can show that if you consider G to be an abelian group, then the F symbols all kind of have a nice structure that you can enumerate. And so, for example, another F symbol that you can write down is F sigma 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 GH. And this is going to be pi. This is a U1 thing. So, okay, so this is the data that specifies that there's also other non-trivial F symbols which I'm not going to write down.
And epsilon is
This is the Frobenius indicator.
plus or minus
It's
1.
plus or minus 1. And the nice thing about this kind of fusion category is that the center Z of A is has a nice intuition. What you can do is you can take this group G and you can consider G gauge theory, and the center is obtained by gauging permutation symmetry of that G gauge theory. So, for example, if you want to consider G equals E2, then this is the topological. This is the G gauge theory with these anyons, and you can see that because these are bosons, you can have a permutation that swaps E and M. So this is a topological order and has a global zero form symmetry, Z2 symmetry that swaps E and M. And that's because in the BF theory you can exchange the gauge fields. Okay, so that's a reason why this has a nice intuition, because you can always get the center from taking some G gauge theory and then you gauge it via permutation. So for example, but you can have multiple permutations. So for example, if you take B equals Z2 times Z2, then the G gauge theory will just be Z2 times Z2 gauge theory. And that has two different kinds of permutations. One is just the usual EM duality of each gauge theory. And then the other is kind of an off-diagonal duality. And so this will be diagonal, and this is off-diagonal. There are many other permutation symmetries, but you can show that they're all equivalent to one of these two upon relabeling. And you can see that these two are different because the anion that's invariant under this permutation is a fermion, and the anions that are invariant under this one is generated by bosons. Because it's E1 and 2, they break trivially each other with bosons.
Is there an easy way to see why the topological order in one dimension is this realized by gauging some anion exchange of a G gauge theory?
Yeah. So one way to do it is just to take the center explicitly, say string that, and then compare it with gauging, and then you find that they're the same.
Is there a nicer way? If not, that's fine.
Yeah, I think that the intuition comes from, like, because this is a symmetry that has to do with in 1 plus 1D is a symmetry of systems that are invariant under gauging, and the bulk PTQFT, that's a kind of a EM permutation of the Wilson-Tibbs lines. But if you want to be rigorous about it, then you can see that they match when you compute them in these two different ways. Yeah.
So, what does I enter?
Yeah. So the chi. So this is diagonal bifurcated. So as I mentioned, chi is any function that's a symmetric bicharacter, so it satisfies these properties. So in particular, because of this, you only need to define kind of chi on the generators and their cross terms, right? Chi on any other group element. So this is Z2 times Z2. This is the generator, the Z2 times Z2. This is their kind of chi between the space. And any other chi on any other kind of pair group elements can be obtained from this. So by diagonal, I mean that this is going to be 2 pi I over n for Zn times, let's just restrict to Z2. And then this is 1, for this is diagonal. And off diagonal, I just mean this is 1, this is. So they're different F symbols because the bicharacter plays a role in F symbol. So then.
Could you make all chi's 1?
Huh?
You cannot make all chi's 1.
If you make all the chi's 1, this won't be unitary. So there are certain constraints on the possible kind of choices for these three values.
What won't be unitary? The theory is not unitary?
The F symbol, you want the F symbol to be unitary because it's kind of like a change of basis, so you want this to be unitary.
I thought this is a non-invertible symmetry.
Yeah, it's not invertible because meaning it's a matrix that has, remember I had F, A, B, C, E, E, F. So this is a matrix. You want that to be unitary.
Why? It's just the fact of some fusion category thing that I don't understand.
Yeah, it's kind of a change of basis between states in a degenerate subspace. So then you want.
I see. So these two indices somehow couple to the states. And
yeah, because these label the fusion outcomes. Right? So, yeah. Okay, so the chi's determine the permutation symmetry that you want to gauge. And what is epsilon? Epsilon is, so if you gauge any symmetry of this topological order, you can always stack with the Z2 SPT, because this is gauging a Z2 symmetry, right? This is, if you do it twice, you come back to itself. This is Z2 symmetry. Before you gauge Z2 symmetry, you can always stack with the Z2 SPT. Because the classification of Z2 SPT is in 2 plus 1D is Z2. There's a choice, and if you stack the non-trivial SPT, that changes epsilon from plus to minus. And what that means is, we know that the Z2 SPT is kind of characterized by the fact that its defects have spin I. So then that will change the F symbols, and it will also change the topological spins of the defects associated with the Z2 permutation symmetry.
What does it mean to stack with an SPT?
Yeah, so that means that before you gauge the symmetry, you add the action of the SPT to the action.
And then
yeah, and then you sum over. Yeah, exactly. Right, and then if you think of microscopic lattice models, you can think of just stacking with the SPT and like gluing the defects of the SPT with the defects of this permutation symmetry, right? Because you can have defects where an E anion can come across to become M, and then you glue the SPTs with these defects. And then basically it just changes the topological spins of these defects.
So in this example, we have 4 different choices.
Yeah, so there are 4 different Z2 times Z2 kind of Parmesan fusion categories, because there's 2 choices of chi, and there's also 2 choices of epsilon. So that gives you 4 different kinds. And 4 different kinds of 2 plus 1D topological orders. Okay.
That's a stupid question. Maybe you say that already, but what is sigma?
Oh, sigma is the dual. So it's a
duality
defect.
But why would G act on duality defect even duality defect?
Oh, so you can think of this as, for example, if you implement this as gauging, then you can choose Dirichlet boundary conditions for your gauge field at the defect, and then that will just kind of absorb the. Another way to think about it is here. If you want this to be true, right, then the idea is that you can, if you want 1 to be as part of the outcome, then this means that you could have snuck in a G here, and it should also participate in the outcome, et cetera, et cetera. So this would be consistent with this citation.
It seems like you're assuming there's 1 sigma. Is that right, or am I misunderstanding?
So in the fusion category, there's 1 sigma. Now in the gauge theory, in which with the Z2 permutation symmetry, there are actually multiple sigmas. There are multiple defects. You can think of there's a kind of bare defect, and then there's a defect that has a anion sitting next to it, et cetera, et cetera. And those very non-trivially with anion like EM.
Well, as you explained, there are multiple different EM dualities. You can imagine the duality defects.
Yeah, so by the multiple different permutations, right? So then, but each of these are associated with a different fusion category. Because the fusion category takes in all of these pieces of data. So once you specify the F symbol, you specify chi, you specify epsilon, that specifies which permutation symmetry, and that specifies whether or not you accept it.
Thank you. That helps.
Okay. But I chose Z2 times Z2, but you can choose any of the other group. And you will find that you will also have some G gauge theory, and then you can get the center by gauging an EM permutation, or not necessarily EM, but some permutation symmetry.
Something terrible would happen if I put a Benito loop in there.
Well, you might not be able to solve the pentagon equations.
Right. That's certainly true. Like
there might not be a solution to it. Okay. So in this case, because the center takes this convenient form where it's obtained by gauging a zero-form symmetry of some abelian gauge theory, you can actually split this into two steps. This problem of finding the magnetic Lagrangian algebra into two steps. The first question that you want to ask, and this will be, so there are kind of two obstructions. And this is kind of natural because actually, if you gauge the Z2 symmetry, you get some complicated non-abelian topological order once you've gauged the theory. But all of the information in the complicated topological order after you gauge the symmetry is already encoded in the symmetry enriched topological order, right? So you could have this information packaged more nicely in this way. So you can, that's kind of the intuition. The first obstruction is that you can look at the G gauge theory, and there needs to be a duality invariant magnetic Lagrangian subgroup of the G gauge theory. This is a Lagrangian subgroup because your G gauge theory is abelian, so this consists of abelian excitations. And you need it to be invariant under the permutation symmetry that's given by your F symbol. If this object doesn't exist, which is pretty easy to check because Lagrangian subgroups are easy to find, then you already know that your symmetry is anomalous. If you pass this level obstruction, then you really need to gauge the Z2 symmetry and then check that there exists a magnetic Lagrangian algebra. This is a Lagrangian algebra of the gauge theory. This only requires information about the bicharacter, whereas this also requires information about the protein nature, because the permutation symmetry only encodes bicharacter.
So this is the Lagrangian algebra of the gauge theory.
Yes. So this is LM of gauge theory.
LM of the gauge theory.
Yes. And which is really the center. Okay, so this is easy to check. In particular, what one can show is all of the Lagrangian subgroups of this abelian gauge theory are generated. So now let's consider Zn times Zn. G.
Sort of interrupt these abstractions
So these are abstractions to the existence of an LM, which means that if an LM doesn't exist, then it's anomalous.
But you can always gauge, right? You can always gauge the subgroup.
Yes, but once you gauge it, you might find that there's no magnetic Lagrangian algebra, because that theory will have a well-defined LE. There might not be an LM. But then the idea is
But
this is
the permutation symmetry itself is not an
no. And so but this is kind of hard to find, right? So this provides an easy check that can already throw out a lot of examples, which is why we want to use it. So if you use G equals Zn times Zn, then what you can show is that all of the magnetic Lagrangian subgroups of Zn times Zn gauge theory are generated by anyons of the form M1 E2 to the P and M2 E1 to the minus P, where P is in 0 n. You can see that these braid trivially with each other because their braiding phase, well, the P cancels with the minus P. So these braid trivially with each other, and they're both bosons, and they generate all of the magnetic Lagrangian subgroups of Zn times Zn gauge theory. And you want to check whether or not this is invariant under these two dualities, right? Because you can show that for any Zn times Zn, you can have an off-diagonal and a diagonal bicharacter. This is like Zn times Zn SPT labeled by P within 0 and n, because we know that there are n 1 plus 1 Zn times Zn. And now if you go through this exercise, what you'll find is if we look at the diagonal duality, that will map M1, E2 to the P, that will map that to E1, M2 to the P under that duality. You need this guy to be generated by this. So you need this to be M2 E1 to the minus P to the P. So this is M2 to the P, E1 to the minus P squared. But you need these guys to be the same, so that means P squared equals minus 1 mod N. That means that only abelian groups such that there exists some integers such P, where P squared equals minus 1 mod N, can it possibly be anomaly free. For all other integers, it has to be anomalous. And this recovers properties that people had already found using explicit gauging from the Lagrangian perspective. So then what we can do is we can restrict to the Zn times Zn where there exists such a P. So those are called, if n is odd, then they're products of Pythagorean primes. But there's a well-defined kind of understanding of the ends that obey that property. So then we'll look at those particular groups, and then we can gauge the theory and then try to find an LM. For the particular case of Z2 times Z2, right, we can have 1 squared is minus 1 mod 2, so that solves it. And what you can show is that for both of these y characters, if epsilon equals plus 1, then it's anomaly free, because you can find a LM of the gauge theory. But if epsilon equals minus 1, then this diagonal one does not have enough bosons to get an LM, and then you can show that it's anomalous. So that's the Frobenius indicator. Remember that whether or not you stack the Z2SVT before you gauge the Z2 symmetry. And it plays this role in that. So you can show that, as you mentioned, for Z2 times Z2 Carolyn-Zhang duality, there are 4 flavors of symmetries. 3 of them are anomalous, and 3 of them are anomaly free, and 1 of them is anomalous. The one that's anomalous is the one with epsilon equals minus 1 in the diagonal boundary. And you can do that from, well, Z2 times Z2 passes this one, but then you need to check, compute the spins of this topological order, and then I can show that from that method that this one is anomalous, or Frobenius because it's minus 1.
Do all these examples have a Lagrangian simulation where you can explicitly just focus on? Are they all some free PTQFTs, Gaussian?
Well,
looks like.
But you can do this with any fusion category. For example, you can take as input like the Fibonacci fusion category, and then Fibonacci fusion category, if you take the center, is double Fibonacci. That has a unique Lagrangian algebra, which is 1 plus top r, which is LE, and then that's the reason why it's anomalous actually, because there's no LM.
And does that have a Lagrangian?
Well, yeah. Well, I'm not sure how to write that.
So it's not known, or you just not known, or you know that there is no Lagrangian, it's just an abstract.
Yeah, there's some Lagrangian formulation of this topological order, but then I'm not sure from that formulation how to actually get this data, whether or not there's an LM or LE. You would have to like look at the.
Is it correct to say that you have kind of a formalism where you can determine whether or not there's an anomaly?
Yes. Well, it's
a
a
very
hard
complicated
formalism,
formalism,
but it's a
which I don't understand.
Yeah.
But,
the complicated formalism is, well, the summary of the formalism is you take the 2 plus 1 PTQFT, and then the symmetry defines an LE, and then you look for some other gap boundary that intersects trivially with that gap boundary. And if you look at the ones like double Fibonacci, where there's only one gap boundary, there certainly isn't another one that intersects trivially, so it's clearly
So in this example you gave, what is the symmetry A?
That is the
That is the Z2.
Z2 times Z2.
Z2 times Z2.
So the G takes value of Z2 times Z2, and then you have a duality object, which is non-invertible because it gives you a sum.
But then there's this exchange Z2.
Oh, that's because this is in the 1 plus 1D theory. It has this symmetry. Then you look at the how do you get this the symmetry TFT, which is a topological order in 2 plus 1D. You can get that by gauging a CM duality of Z2 times Z2 gauge theory. So that's the method for getting this Z of A in this context for this symmetry. For other kinds of more complicated fusion categories, you can't get it from gauging symmetry of Z and gauge theory.
So in these examples, in the instances you can gauge it and it's anomaly free, do you know what the dual symmetry is?
So that would be the dual symmetry would be the symmetry defined by this LM.
Yeah, the fusion category describing the topological defects of the LM boundary.
Yeah. Huh?
What is it? Or do you know? And if you do know, can you give a simple example of what it is?
Well, for this one, it would just be rep C2. But in general, right?
For the top REM.
Yeah. So yeah, it will be some other fusion category. I don't know if it has a nice kind of.
Okay.
Can you remind me the relation between that sigma and the anion responding to the symmetry, responding to the duality's symmetry effect?
Yeah. So this so when you gauge this EM permutation symmetry, these defects are so for there's going to be 2G kind of duality anions that all have quantum dimensions square root of G, and those come from those will come from the permutation defects. So you can think of those as related. Related in the sense that okay, so for example, for Ising, okay, so they are related in the sense that for they have dimension. Okay, they come from the the defects of the EM permutation, which is the thing that you add onto the Zebulon gauge theory. But yeah.
So you can move that anion to the boundary, does it become sigma? Is this sigma?
Yeah, exactly. So it does become sigma when you move it to the boundary. You can think of, like, if you want to construct a stringnet model, then all of these 2G sigma type anions have the sigma stringnet. They become sigma as you bring them to the boundary. Yeah.
Another example, suppose G is just a Z5. For Z5 gauge theory, I think there's an anion permutation symmetry at multiply. So for G5 gauge theory, the anions can be labeled by 2 integers. I think there's a permutation symmetry that multiplies both anions by 3. It's a quite a strange permutation symmetry. Is that also included in this construction?
Yeah, so that will not be included because if you multiply each anion by 3, that will actually be anomalous for Z5 because then you can show that the quantum dimension of the sigma is square root of 5, and you can show that whenever this thing is not an integer, it's already anomalous. But you can certainly take that permutation symmetry and gauge it if you want to. But what you'll find is that there can't possibly exist a mechanically bound anomaly.
You said that symmetry is anomalous. Which symmetry? Oh, the A symmetry is anomalous.
Z5 together with the duality defect. It has to be anomalous.
But the anion permutation symmetry itself is not.
The anion permutation. So are you saying like E goes to what?
3.
E third. And then M goes to what? M third. And so then this will take EM, which has topological spin spin e to the 2 pi I over 5 to e to the 2 pi I over 5 times 9, which is minus e to the 2 pi I over 5. Alright, so that's a time reversal symmetry.
Okay. There are also similar unit examples. Like U1 level 12 multiplied by any by 5.
Yeah. But here it's this is the chi in this case will always correspond to a unitary symmetry. You can show that. In fact, like if you, that's why you can gauge it, because the anion that it maps between it will have the same topological spin, so they can make topological spin of the resulting anion of the gauge theory.
I guess my question is, for ZN gauge theory, there's obvious anion commutation symmetry. That's just some kind of Z4 symmetry. But for some kind of ZN gauge theory with particular anion, there can be some strange anion commutation symmetries.
Yeah.
I'm asking if I gauge those anion commutation symmetries, do I have a construction of the fusion category A?
Those might be anomalous. And so if they are anomalous, then you can't gauge. So
They may not be anomalous.
in fact, yeah, I'm not sure how to gauge this time reversal symmetry in this particular case, because usually you would want to map them between anions that have the same topological spin, so that in the gauge theory there's a kind of, in the gauge theory you want to identify orbits under the symmetry, right? But if these have different topological spin, then
this is a bad example, it's my fault. But another example is U1 level 12 multiplying the anion by 5. That's a unitary anion commutation.
Yeah. Then if the symmetry doesn't fractionalize or anything, then you can presumably gauge it. But U1 level 12 that actually has a gapless boundary. That doesn't have a gap boundary. Right?
U1 level 12 with U1 level minus 12.
Okay. If you do U1 level 12 with U1 level minus 12, then it will be some Dirac-Witten theory. Because it's a abelian gauge theory. And then you can gauge a permutation symmetry, and then it will be one of these. But if you just do U1 level 12, then it doesn't even have a gap boundary, so it's certainly not the center of any fusion category. Okay. So maybe I should remark now that we see that even for the off-diagonal case, it can accommodate a Frobenius-Schur indicator of -1. And that's actually kind of surprising, right? Because Frobenius-Schur indicator of -1 means that you're stacking the Z2 SVT before you gauge Z2 symmetry. The Z2 SVT already has a Z2 anomaly for the edge theory, right? So it's kind of weird that that you can actually be anomaly free even if you have Frobenius-Schur indicator of -1. For example, if you just take the Z2 SVT on its own and you gauge Z2 symmetry, it will give you the anomalous Z2 symmetry. But now, when you gauge the SVT but you stack it with some topological order and you gauge Z2 symmetry, it's somehow anomaly free. And the idea there is that sometimes if you have an anomalous symmetry, you can extend the symmetry. So you add things to the symmetry, and even though it's anomalous on the original symmetry, with extended operators, it's no longer anomalous. And we're very familiar with that in the case of groups, right? Because we understand by group extension, for example, if you have an anomalous Z2 symmetry, and this is related to the third method now. If we have an anomalous Z2 symmetry, then we know that omega GGG equals -1. But now if we extend the symmetry, so it's no longer Z2, but it's now Z4, then this is not anomalous, because now now you take G to the 4 equals 1, and you can show that this is just a coboundary. And so that's the theory of group extension, is that you can, if you take some group that has an anomaly, you can extend it to another group that's anomaly free. In this case, it's a non-invertible extension that generalizes the group extension to make the original Z2 symmetry anomaly free when you add new elements to the symmetry that makes it non-invertible. So that can be applied. So then the approach is as follows. You look at the Z2 SVT, And what you can show is that for any Z2SPT, it can have a decorated domain wall construction. And the decorated domain wall construction comes from the fact that at this domain wall of the Z2 symmetry, so suppose that this is two vacua, where this is like you act with G on this side. Here, the order parameter is 0, so you expect it to be a Z2 symmetry. But it's weird because it doesn't take the size of your two sides to each other. And this was explored by Hassan, Komargatsky, and Thorngren in 2020. And there was also a paper by Cordova, and others in 2020 as well, that discuss how if you have a Z2 symmetry, then what you can do is you can apply the Z2 symmetry everywhere, so that will flip these two vacua. And then you do a CPT transformation. So P flips it across this axis, and so that will bring it back to the original state. And you can see that CPT acts now locally on these sides, but at the domain wall, it's a local transformation on that domain wall. And so if you have a Z2 symmetry globally, then that will map onto a time versus symmetry on the domain wall. And so this Z2 SPT that you're stacking in 2 plus 1D has a decorated domain wall construction. Then the Z2 domain walls are decorated by T SPTs. And we know that there's a Z2 classification of time versus SPTs in 1 plus 1D, which is aligned with the Z2 classification of Z2 SPTs in 2 plus 1D. So you can decorate with the trivial SPT or the non-trivial T SPT. Whenever you have a decorated domain wall construction, we can now look at the boundary of the 2 plus 1D theory. So this is the boundary of the 2 plus 1D theory. And you act a symmetry. Then what you'll do is you'll deposit a TSPT on this half where you've acted symmetry. So this is now decorated with the TSPT. And we know that in 1 plus 1D, the TSPT carries a converse degeneracy of the defects. So we need to ask, so now if we want this symmetry, this is the original anomaly of the Z2 symmetry. And we need to ask, what kind of quantum mechanics can we add to this defect to cancel the converse degeneracy? And that quantum mechanics will, in general, modify the fusion rules, thereby extending the symmetry, which is exactly what I mentioned. One way to extend it is using the Z4, but then the thing that we want to check is, if we do a non-invertible extension, can it cancel this T squared plus minus 1? So what we need to check is, what is the quantum mechanics of the defect, of the sigma defect in 1 plus 1D? It turns out that that's this qubit, and we know that it's a qubit because the dimension of the Hilbert space is 2, because that's the quantum dimension of the sigma. And that, and what you can show is that the quantum mechanics that ends the sigma defect is just a qubit. And for the diagonal and off diagonal, so this qubit has a Z2 times Z2 symmetry acting projectively. And these Z2 symmetries come from the fact that the sigma can be thought of as gauging a Z2 times Z2 symmetry. Well, because the original symmetry was Z2 times Z2 together with sigma, so the defect also has Z2 times Z2 symmetry. And the diagonal, and so if it has the projective representation of Z2 times Z2, we can generate them by the poly X and poly Z operators. In the diagonal case, the time reversal symmetry on the defect does exchanges these two Z2 symmetries. Whereas in the off diagonal case, one can show that it maps X to X and Z to Z. So it doesn't act on the Z2 symmetries. Okay. understand whether or not this qubit can realize a t squared equals -1 that's compatible with the symmetry action. Because if it can realize the t squared equals -1, then it can cancel this anomaly. And then you can show that actually that corresponds to a case where the non-invertible extension trivializes the Z2 anomaly. On the other case, if this qubit can't realize a t squared equals -1 that's compatible with the symmetry action, then you can't cancel this anomaly. So this non-invertible extension does not trivialize the Z2 anomaly. And so what you can show is that the diagonal case, what you can show is that the off-diagonal case, you can have a T symmetry that permutes that leaves these two invariant, and you can just do that y times k, sigma y times k. It leaves these two invariant upon conjugation, and it squares to -1. On the other hand, you can't find a T symmetry that squares to -1 and also permutes these symmetries. So then you can already show that this T squared equals -1 is incompatible with the diagonal one, which is another easier check to show that the Z2 times Z2 Karamazani duality with Frobenius Schrödinger indicator equals -1, which means that it has this non-trivial anomaly, and diagonal bicharacter is anomalous. The nice thing is that this generalizes to higher dimensions and is very powerful in higher dimensions. And the reason is 2 plus 1D fusion categories are very diverse, because 2 plus 1D topological orders are also very diverse, because you can have anyons. But actually topological orders are simpler in higher dimensions. So for example, if you want to work with 3 plus 1 dimensions, symmetries in 3 plus 1D, you want to look at topological orders in 4 plus 1D, right? Yeah, topological orders in 4 plus 1D. And one can show that topological orders in 4 plus 1D are all obtained by gauging some zero-form symmetry of an abelian two-form gauge theory, possibly with a fermion. So this construction of looking at the SPT of a zero-form symmetry and then seeing if you can do this cancellation is very, very powerful in 4 plus 1D. And that's the content of the last work, which then talks about Karamazani dualities in 3 plus 1D, where you have G associated with an abelian one-form symmetry. And you also have a gauging symmetry that's kind of like the sigma, except now this is Z4. And you can look at, and then you can get the centers, or get the 4 plus 1D complex. This is a 3 plus 1D.
Is this sigma constructed by half gauging, Tucci?
Yes. But they're cyclic conditions. And so you can also now consider, so to study the 3 plus 1D symmetry, you study 4 plus 1D abelian gauge theory with the Z4 EM permutation. And it's EM is Z4 because in 4 plus 1D, the EM permutation, well, now you have like K, now you might have some N over 2 pi. The action, or the, action will be like this, where these are now Q-form, but this is antisymmetric, right? So instead of swapping E and M, you need to take BE to BM, and BM to minus BE, so it's actually a Z4 symmetry. And you can consider 4 plus 1D Z4 SPTs, like how you consider 2 plus 1 Z2 SPTs. And you can actually then consider the analog of Frobenius Schrödinger indicators in these 3 plus 1D non-invertible symmetries to show that gives additional anomalies in certain cases. So then this anomaly cancellation by symmetry extension method is very powerful for this. Let's see. Okay.
What about the FS indicator is reflecting cases?
Yeah, so there's going to be, so what you can show is for N, so if we consider the N, G equals the N, For odd n, you want to consider bosonic Zn SPTs and 4 plus 1D. And if you validate the cobordism group, then you'll find that there's a Z4 times Z4 classification. 4 comes from incohomology and 4 comes from BI cohomology. Those will be FS indicators. And then for even n, you actually want to study the fermionic Zn SPTs for reasons you probably know. And in that case, you get a Z4 classification as well. So then those will give, Z4 FS indicator. Because it's powerful, you can also study other kinds of, you can potentially classify all of these kinds of symmetries in 3 plus 1D, because you can consider all of the obstructions of 4 plus 1D topological orders due to these kinds of FS indicators. And they all, 4 plus 1D topological orders all take this nice form, so you can study them systematically. Okay. So I have some future directions. It's already 5. Yeah, I guess the future directions is actually, it's very interesting to study these, the process of gauging one-form symmetries on the lattice. There's a lot of subtleties, especially if you consider more general stacking with SPTs and what people call STN gauging. Another aspect is you can construct lattice models that have this duality symmetry by generalizing the Ising model to Zn one-form symmetries in 3 plus 1D. So you can construct H equals lambda H0 plus lambda prime H1, where these are related by gauging, and then consider the point where lambda equals lambda prime. So it's kind of like Ising. And because there are the one-form SPTs, because we're studying one-form SPTs, the classification is non-trivial in 3 plus 1D. You can expect there's actually kind of a non-trivial phase diagram that you can draw for this that we only conjecture would be interesting to do numerics for. It would be also interesting to study where in nature these non-trivial FS indicators come from, because in the Ising model we know the FS indicator is 1. But what kind of models can we write down? What simple models can we write down that actually utilize these non-trivial FS indicators? Or where can we find them? Those are interesting problems. Yeah, but there's out of time, so. Yeah.
So something that kind of confuses me is that, or like it's just sort of counterintuitive, is that at least naively, anomaly isn't really invariant under gauging. So like if I take D8 for example, and then gauge the normal subgroup, then I get an anomalous Z2 cubed.
Yeah.
So like how would this, how could you like explain this in your language?
Well, now we take the gauging as a symmetry. So usually if you gauge a subgroup, you'll get a different symmetry. You get a different theory. But some theories are invariant under gauging. So those are the theories that we'll consider. Or, yeah, you can construct models like that, which interpolate.
I guess what I'm asking is like, you could take a totally non-anomalous D8 symmetry, but somehow it should actually be anomalous. Like, because or somehow it's like related to an anomalous symmetry, and like Z of A is like invariant under gauging. So like.
Yeah, that's saying that the A is defined by the symmetry you're interested in. So whether this is D8 or whether this is some other group, that will determine LE. So even though ZA is the same, the LEs will be different. And so then the existence of LM will also depend on the choice of LE. But your point is actually that's very useful, because that's exactly how we determine whether the defect theory in 3 plus 1, the defect in 3 plus 1 will be 2 plus 1D, whether those carry an anomaly that can cancel the anomaly corresponding to those 4 plus 1D SPTs. We use that.
In the case of Maxwell theory, there's also this non-invertible duality. Do you know what is the Greenwich theory?
We only discuss for discrete groups.
Yeah, this is discrete.
Oh, if you gauge a Zn subgroup, for example?
It's just gauging.
Yeah, so then you would look at that would also be a Z4.
Yeah, but
Yeah.
do you know which elements?
So I think that will be the trivial FS indicator in free Maxwell theory, because it's kind of like this. It's like the clock model, except you take two, the Zn, and so that will actually realize a trivial FS indicator. That's why I said it will be interesting to try to find which models in nature you might find a non-trivial FS indicator.
So you could actually show that it's
Huh?
So you could actually prove that it's
The FS indicator?
Yeah.
I think we conjecture that it's trivial, but like we didn't compute the fusion rules or whatever to show that's trivial. Yeah. Yeah.
Do you know any examples of non-invertible symmetries in previous being about Maxwell theory?
Yeah. So you can that Maxwell theory will correspond. So okay. So this is
Can you repeat the question? Sorry, I didn't hear the question.
Do we know any examples of A+1B theories with non-invertible symmetries other than Maxwell theory?
Yeah, so that's related to one of the kind of directions I was talking about, because Maxwell theory is, so if you take the abelian one-form symmetry in 3 plus 1D, that's the trivial one-form SPT. So in general, these are classified by, if you take Zn one-form symmetry, if you take Zn one-form symmetry in 3 plus 1D, those will be classified by either n or 2n, depending on if n is even or odd. If you take the trivial SPT, and then you can show that, okay, under gauging, it will have some symmetry, and then if you construct something like this, it will flow to U1 Maxwell theory, free Maxwell theory. But if you take the non-trivial SPT, then, for example, if you take P is, so P labels the SPT, or like 0 to n. If you take P is around square root of n, then we have some arguments one can show that this doesn't flow to free Maxwell theory in the IR. And so, but it still has this like duality symmetry.
We don't know.
Well, the hypothesis is that I realize this, so we know that there's kind of this phase diagram where this is n, and this is the coupling, and this is like Maxwell, and these are first order transition lines, and then the hypothesis, this is for n, p equals 0, and the hypothesis is that as you increase p, this shrinks, and that for p sufficiently large, it goes back to this first order transition line. But we haven't verified that. And then presumably if it's not anomalous, you can also add perturbations to make it gapped. And that would be quite interesting to get a gapped 3 plus 1D, because we show that some of these are not anomalous 3 plus 1D non-invertible symmetries. So in principle, one can get a gapped theory that has symmetry.
You could just look at non-linear gauge theory.
Yeah, exactly.
Disconnected gauge theory, something like n plus.
Or even simpler, just finite non-abelian gauge theory, where the group is not abelian finite.
Yeah, we can also do that.
No, but you know everything about those theories.
So you just ask.
Yeah, we just asked for an example. You didn't ask for
I think some of the papers say that, so some papers, I think there are papers that claim that like n equals 4 superangles would give request to the complex effect gauge coupling tau equals pi has some solid duality property. Something that to construct it. I think it's like way maybe or something. Superangles better than. And I think it also has
I mean, a bunch of nonlinear sigma models in 3 plus 1D will have it too. If you have non-abelian vortices, so if pi 1 is not abelian, pi 1 is target space.
Sigma 1, sigma 1.
Yeah, but that's pi 1's abelian. But have pi 1 be not abelian, and
Yeah,
it'll
but
be
that's pi.
non-invertible.
It still has no invertibles.
Oh, I see.
Coming from
there's
pi.
some recent papers on
So I guess the answer